So this is a continuation of the financial seismology discussion. You can treat this sort of as an appendix. We mentioned in the prior slide signal performance, and I wanted to talk a little bit more about that. A signal is a singular event. It's not a buy, a money management, and a sell, which is a full strategy, but an individual, some kind of individual event that gets you into a trade or out of a trade. But um, it's a singular event. It's not a full trade. So these are some of our definitions, where a strategy is a combination of signals that leads to an entry and an exit. And that's where you measure Sharpe ratios and profit factors and whatnot. But what do we measure for a single signal? We want to be able to use signals that have a predictive edge, because if we don't, then our returns might be no different than the market. We're not going to gain an edge over our benchmark. So what we defined here is a model with a initial edge, a peak edge, and then a decay back to zero, because every signal that happens, every signal we can define is going to eventually have no effect. Whatever edge you had is going to wear off over time. So here's our definition of edge and duration. This is a case of somebody who came in with a signal that they really liked. They thought it had a significant edge. Again, edge is different, is a measurement of deviation from random. So 50-50 coin toss is a random, a zero edge, and this would be additional edges on top of 50%. Well, it turned out the background edge was significant. So in this graph, we're showing the background edge here, and the darker line being the edge on their signal, which is called ML1. And you have to subtract the background in order to see what the reality is. And the background in this case is a 2% edge initially, which decays over time. This is the number of bars going away from the initial signal, and it decays to the point where it has almost no effect. So that's our definition of edge. Duration is how long it takes for the signal edge to go back to zero. So yeah, well, I'll include this section in the discussion of edge. It sort of falls into the same appendix of the talk. Markets display what are called a fat tail distribution of returns. What's shown here is a normal Gaussian distribution, and this line that I'm tracing out, with 1 standard deviation, 2 standard deviations, 3 standard deviations from a mean. But then these yellow areas that are marked here are what we call fat tails, and the market exhibits this in a way by producing many more events that have larger deviations from larger standard deviations than one would expect. And so why is that? Well, as it turns out, I put this to a fellow that was working on his PhD degree, and we were talking about stochastics pursuit as maybe being the reason for these fat tails. If investors are chasing price, then obviously when you've got a very large standard deviation move, that's going to attract the most attention of all, either an up move or a down move. And if investors are chasing price, they're going to react more strongly the bigger the move is. So that might account for these fat tails. Well, he did a study. So on this graph, it shows if there was a perfect normal distribution, you'd have this diagonal line through the chart would be the measured versus predicted standard deviation graph. This is from 4 standard deviations, predicted versus actual, and the blue line through here is my measurement using lots of data, millions of examples, I measured the deviation from a normal distribution, and these are our fat tails. As you get out even just past 2 standard deviations, the tail gets fatter and fatter on both ends, either down moves or up moves. And so this stochastics pursuit model actually predicted that, at least it predicted this, very, very closely predicted the fat tails on the upside. Didn't quite manage it on the downside, but of course down moves are a lot scarier than up moves, so perhaps it didn't quite accommodate that. But interesting enough, stochastics pursuit seems to be the reason for the fat tail distribution. So we correct for that in a lot of the work we do. We correct for the fat tails. Here's an example of standard deviation bands. People that like to use tools like Bollinger Bands and whatnot they're looking at standard deviation bands, and so the inner band here is 2 standard deviations without correction, and the outer band is with correction. So just to show how it affects, normally a 2 standard deviation band would be hit 2.275% of the time, and without correction it gets hit 3.6%. This is 20 years of S&P 500 daily scale, so it's quite a lot of data. And the bottoms got hit 6.4% of the time. But with correction, that goes to 2.7% of the time, which is not quite 2.275, but it's getting closer. And 1.6% for the tops being hit. So the correction takes us in the right direction towards a more classic definition of normal distribution. And just to summarize the basic ideas, technical analysis is derived from complexity theory. That's what we believe we've proven. Extreme feedback is predictive, and there's implications for equilibrium economics. The fact that booms and busts are present and markets tend to organize far from equilibrium might have implications for a more macro view of economics. So with that, I'll wrap it up, and hope you enjoyed the presentation.